Good morning students, this is Latif sir. Today in this video I will discuss about haloalkanes and haloarenes. Haloalkanes and haloarenes. This is the chapter 10 of class 12 chemistry. So first you have to know what are haloalkanes and haloarenes. Haloalkanes and haloarenes are formed by replacement of one hydrogen atom. One or more hydrogen atom, haloalkanes or haloarenes are formed by replacement of one or more hydrogen atom from an aliphatic or aromatic hydrocarbon by halogen atoms. So if you replace one hydrogen atom from an aliphatic or aromatic hydrocarbon, you will get haloalkane or haloarenes, and this is generally represented by Rx, where R is alkyl group and X is a halogen atom. Okay, X means fluorine, chlorine, bromine, iodine. These are X. X is halogen atom. Okay, so the replacement of hydrogen atom in hydrocarbon, in aliphatic or aromatic hydrocarbon by halogen atom result in the formation of alkyl halide or haloalkanes and aryl halide or haloarenes. Haloalkanes are also known as alkyl halide, and haloarenes are also known as aryl halide. Okay, that means if you replace one hydrogen atom from an aliphatic hydrocarbon by a halogen atom, then you will get haloalkane or alkyl halide. And if you replace one hydrogen atom from an aromatic hydrocarbon like from benzene, okay, if you replace one hydrogen atom from an aromatic hydrocarbon by a halogen atom, then you will get haloarenes or aryl halide. Now see classification of haloalkanes and haloarenes. Classifications. So haloalkanes and haloarenes both are represented by this general formula Rx, where X is an halogen atom. Now see classification of halogen derivatives, that is classification of haloalkanes and haloarenes. There are different methods of classification of haloalkanes and haloarenes. First one, on the basis of number of halogen atoms, present in haloalkane or in haloarenes. Haloalkanes and haloarenes can be classified as monohaloalkane if only one halogen atom, only one X means halogen atoms, X means halogen atom like fluorine, chlorine, bromine, iodine, these are halogen atoms. Okay, if only one halogen atom is present in the compound, then it is known as monohaloalkanes. Example of monohaloalkane, C2H5X or CH3Cl. Okay, so this is an example of monohaloalkane. If two halogen atoms are present in the haloalkane or haloarenes, then it is known as dihaloalkanes. Okay, in dihaloalkanes you can see two halogen atoms are present, CH2X, CH2X. So this is an example of dihaloalkanes. And chlorobenzene, this is also a monohaloalkanes. One halogen atom is present in benzene ring. This is a monohaloarenes. Okay, this is benzene ring, aromatic ring. So this is monohaloarenes. Only one halogen atom is present. If three halogen atoms are present in an haloalkane or haloarenes, then it is known as trihaloalkanes. In this compound, three halogen atoms are present. Okay, so this is an example of trihaloalkanes. Okay, so based on number of halogen atoms present in haloalkane or haloarene, haloalkanes are and haloarenes are different type like monohaloalkanes, dihaloalkanes, trihaloalkanes. Okay, now this is second type of classification, which is primary or 1 degree, secondary or 2 degree, and tertiary or 3 degree classification. Okay, so on the basis of nature of carbon to which halogen atom is attached, on the basis of nature of the carbon carbon to which halogen atom is attached, halogen derivatives are classified as 1 degree or primary, 2 degree or secondary, 3 degree or tertiary, or allylic haloalkanes benzylic haloarenes, okay, vinylic, arylic. These are some different types of haloalkanes and haloarenes based on the nature of the carbon atom to which the halogen atom is attached. Okay. So first see primary or 1-degree haloalkanes. Primary or 1-degree haloalkanes. In primary or 1-degree haloalkanes, we can see the carbon atom. You can see the carbon atom. The carbon atom containing the halogen atom is directly attached only with attached is directly attached to only one alkyl group. Okay, if the carbon atom containing the halogen atom is directly attached with only one carbon atom, one alkyl group, then it is known as primary or 1-degree. If the carbon atom containing the halogen atom, if the carbon atom containing the halogen atom is directly attached with two alkyl group or two carbon atom, then it is known as 2-degree haloalkanes. And if 2-degree or secondary, okay, and if the carbon atom containing the halogen atom, if the carbon atom containing the halogen atom is directly attached with 3 carbon atoms or 3 alkyl groups, same or different type alkyl groups, then it is known as 3-degree or tertiary. Okay, so in 1-degree haloalkane, the general formula is RCH2X. In 2-degree haloalkane, the general formula is R2CHX, and 3-degree haloalkane, the general formula is R3X. Okay, and only CH3X means methyl halide. Methyl halide. Only CH3X means methyl halide. Okay, and CH3CH2X is 1-degree haloalkane. Okay, this is 1-degree because carbon atom containing the halogen atom is directly attached with only one carbon atom. Now see allylic haloalkane and benzylic and vinylic and aryl halide. So allylic haloalkanes, if the halogen atom is present, if the halogen atom is present or is attached to the carbon atom which is next to the double bonded carbon, then this type of haloalkane or haloarenes is known as allylic haloalkanes or haloarenes. Okay, so allylic alkyl halide or allylic haloalkane. Okay, if the halogen atom is present at the carbon atom which is next to the double bonded carbon, this is the double bonded carbon, and halogen atom is present, is attached with this carbon which is next to the double bonded carbon. So so this is an example of allylic haloalkanes. Okay, so general structure of allylic haloalkane is CH2 double one CH single one CH2 and X. The halogen atom is attached to the carbon atom which is present next to the double bonded carbon. And this is also example of allylic haloalkanes. Okay, the halogen atom is present at the allylic carbon. This is the allylic carbon, and here this is the allylic carbon. Carbon next to the double bond is known as allylic carbon. Okay, and if halogen atom is attached to the if halogen atom is attached to the allylic carbon, then it is known as allylic halide or a haloarene or allylic haloalkane. And if the halogen atom is present, if the halogen atom is attached to the carbon atom which is next to the benzene ring. Okay, this is the benzene ring, and the carbon which is directly attached with benzene ring, that is this one. If halogen atom is present, is attached with this carbon, then it is known as benzylic halide or benzylic haloarenes. Okay, so if the halogen atom is directly attached to the carbon which is directly attached to the benzene ring, then it is known as benzylic haloarenes. And now see vinylic. If the halogen atom is directly attached to the double bonded carbon, if the halogen atom is directly attached to the double bonded carbon, then it is known as vinylic, then it is known as vinylic halide. And if the halogen atom is directly attached to the benzene ring, if the halogen atom is directly attached to the benzene ring, then it is known as aryl halide, like chlorobenzene. Chlorobenzene is an example of aryl halide. because in chlorobenzene the chlorine atom is directly attached to the benzene ring. It is aryl halide. Okay, and benzene ring CH2Cl, it is benzylic halide, benzylic chloride. Okay, so these are some different types of haloalkanes and haloarenes. Now see general method of preparation of haloalkanes and haloarenes. General method of preparation of haloalkanes and haloarenes. First one is from alcohol. From alcohol you can prepare haloalkanes. This is the preparation of haloalkane first. So from alcohol you can prepare haloalkanes. Alcohol means ROH. This is the general formula of alcohol. This is actually substitution reaction. If you substitute OH from alcohol by a halogen atom, then you will get haloalkane. Okay, and there are different reagents are used. For example, if you use HCl in anhydrous ZnCl2, which is known as Lucas reagent, if you react alcohol with Lucas reagent means HCl in anhydrous ZnCl2, you will get chloroalkane. You will get chloroalkane. Okay, RCl. The OH of alcohol will be substituted by chlorine atom if you treat alcohol with Lucas reagent, that is HCl and ZnCl2. Okay, so this is one method of preparation of haloalkane from alcohol. Similarly, if you use PCl5 or PX3, PX3 means PBr3 PCl3, okay, or PCl5, then you will see that the OH will be substituted by the halogen atom. Okay, there are different reagents. If you use PCl5, if you react PCl5 with alcohol, the OH of alcohol will be substituted by chlorine atom. So this is the major product preparation of haloalkanes. So side products are not important, major product is important. Okay, similarly, if you use SOCl2 in pyridine, SOCl2 sulfonyl chloride, if you react alcohol with sulfonyl chloride, you will see that the OH of this alcohol will be substituted by chlorine atom. So you will get chloroalkane plus SO2 plus H12. Side products are not important. Important is major product. Okay. Next method is free radical halogenation reaction. Free radical halogenation reaction. This is the second method of preparation. You have already studied in class 11 about this process. Okay, if you treat methane with sunlight, if you treat methane with chlorine in presence of sunlight, what you will see? If you react methane gas with chlorine, you will see that the hydrogen atom of methane will be substituted by chlorine atom. So you will get haloalkane. Okay, so this is a haloalkane chloromethane CH3Cl. Sorry, it is CH3Cl. Okay, the hydrogen atom from haloalkane from methane from hydrocarbon will be substituted by one by chlorine atom. Okay, another example is given. This is CH3 CH2 CH2 CH3 N-butane. This is N-butane, not normal butane. If you treat N-butane with chlorine in presence of sunlight or UV light or heat, you will see that the hydrogen atom from N-butane will be substituted by chlorine atom. And in N-butane there are two type of hydrogen atoms, two type of carbon. Two carbons are 1 degree and two carbons are 2 degree, and these two carbon, number 2 and number 3 carbons are 2 degree carbon, and number 1 and number 4 carbon are primary carbon. Okay, so when N-butane reacts with chlorine, two types of halogen derivative or haloalkane you will get, and this will be the major product. Okay, substitution at 2 number carbon will be more than substitution at 1 degree carbon. Now see, addition of halogen halides on alkane, addition of HX on alkenes, addition of HX on alkenes. This is an alkene, one double bond is present in this compound, so this substrate is an alkene. And now if you add HBr or HCl or HI, to this alkene, you will see that the double bond of the alkene will be break, and hydrogen atom and Br atom will be attached with two double bonded carbon. Okay, so using this method, addition of halogen halides on alkenes, you can prepare haloalkane. Hydrogen will be attached with one carbon and bromine will be attached with another carbon. Okay, and this reaction is controlled, or is controlled by Markovnikov rule. Markovnikov rules you have already studied in class 11. That is, the negative part of HBr, that is Br minus, will attach to the carbon which contain less number of hydrogen atom. Okay, the negative part of HBr, that is Br minus, will attach to the carbon which contain less number of hydrogen atom. Okay, and H plus will be attached to the carbon which contain more number of hydrogen atom, and this reaction is governed by Markovnikov rule. But in presence of same reaction, in presence of organic peroxide, addition of HBr to alkene, in presence of organic peroxide, the rule will be anti-Markovnikov rule. Okay, that is, in presence of organic peroxide, Br minus will enter to the carbon which contain more number of hydrogen atom, and H plus will be enter to the carbon atom which contain less number of hydrogen atom. So in presence of organic peroxide, addition of HBr to the alkane, the rule will be anti-Markovnikov rule. Anti-Markovnikov rule. Okay, you have already studied in class 11 about Markovnikov anti-Markovnikov rule. Okay, I am giving one example. Suppose this is the substrate CH3 CH double bond CH2. This is an alkene, and if you want to add HBr to this alkene, the Br minus will enter to the carbon which contains less number of hydrogen, and an H will be entered to the carbon which contain more number of hydrogen. So the product will be CH3 CH Br CH3. Okay, the double bond will be break. Similarly, if you add HBr in presence of peroxide, the product will be, the selection rule will be different. In presence of organic peroxide, the Br minus will be attached to the carbon which contains more number of hydrogen atoms. That is, in presence of peroxide, the Br minus will enter to the will attach to this carbon atom. Okay, the product will be CH3 CH2 and CH2Br. Okay, this is in presence of peroxide, and remember that the peroxide effect or anti-Markovnikov rule only applicable in case of hydrogen bromide, not in case of hydrogen chloride, or not in case of hydrogen iodide. Okay, anti-Markovnikov rule or peroxide effect is only applicable in case of addition of HBr to alkene, not in case of HCl, in case of HI. Okay, in case of HCl, in case of HI, always you have to remember the Markovnikov rule. Okay, now next method, Finkelstein reaction. Important reaction. This is the halogen exchange reaction. Preparation of haloalkane from another haloalkanes. Okay, you can prepare haloalkyl iodide from another haloalkane using Finkelstein reaction. In this reaction, haloalkane is treated with sodium iodide and in haloalkane the halogen will be chlorine or bromine, not iodine. Okay, so in Finkelstein reaction, alkyl halide is treated with sodium iodide in presence of acetone medium or carbon disulfide medium. You will see that halogen atom will be substituted by iodine. Okay, so in Finkelstein reaction, using Finkelstein reaction, you can prepare alkyl iodide from another halogen, alkyl halide, from alkyl chloride or from alkyl bromide. You can prepare alkyl iodide, and the reagent is sodium iodide. This is the reagent in Finkelstein reaction. Now Schwarz reaction, it is also halogen substitution reaction, preparation of halogen exchange reaction, preparation of haloalkenes, preparation of fluoroalkane from another from other alkanes, from other alkyl halide. Okay, so for example, if CH3 beer is treated with inorganic fluoride like AgF or COF2 or Hg2F2 or SbF3, if you react an alkyl halide in which halogen is in which halogen is chlorine, bromine and iodine except fluorine, with inorganic halogen inorganic fluoride like AgF, Hg2F2, you will get fluoroalkane RF. The halogen atom will be substituted by fluorine atom, and this reaction is known as. Next method, Hunziker reaction. Hunziker reaction also important reaction. So using Schwarz reaction and Finkelstein reaction, you can prepare alkyl iodide. Using Finkelstein reaction, you can prepare alkyl iodide, and in using Schwarz reaction, you can prepare alkyl fluoride from other alkyl halide. Okay, or from other haloalkanes. Now next method is Hunziker reaction. Hunziker reaction also important reaction. In this method, you can prepare alkyl bromide from silver salt of carboxylic acid, CH3COOAg, that is RCOOAg, silver salt of carboxylic acid. When treated with bromine in CCl4 medium, when treated with bromine in carbon tetrachloride CCl4 medium, you will get RBr, alkyl bromide. Okay, so when silver salt of carboxylic acid is treated with bromine in carbon tetrachloride solvent, you will see that this COOAg group will be removed, and you have to add one bromine to the alkyl group, that is CH3Br, and the side products are AgBrCO2. Okay, now see, so these are some preparation of haloalkanes and haloalkanes. Okay, all are important. Now see physical properties of haloalkanes and haloarenes. In physical property, only you have to read about melting point and boiling point of haloalkanes and haloarenes. First, if the alkyl group is same in haloalkanes and haloarenes, if the alkyl group is same in haloalkanes and haloarenes, then the order of melting point and boiling point is alkyl iodide greater than alkyl bromide greater than alkyl chloride greater than alkyl fluoride. If the halogen alkyl group is same, then the order of melting point and boiling point is alkyl iodide greater than alkyl bromide greater than alkyl chloride greater than alkyl fluoride. Okay, and if the alkyl group is different, the halogen atom is same, then the order is, you have to remember, always tertiary, always primary alkyl halide has primary, or for isomeric haloalkanes, long chain alkyl halide or haloalkane has more boiling point than branch chain alkyl halide or haloalkane. Okay, so this is the second, this is normal or 1 bromobutane, and this is 2 bromobutane. Okay, this is 2 methyl 2 bromo 2 methyl propane, and this is 2-methyl 2-bromo, and this is tertiary. This is tertiary haloalkane. This is primary, and this is also primary. But here one branching is there, and here in this compound two branch are there. Okay, as branching increases in the substrate, melting point and boiling point will be decreased. Okay, so remember that always long chain hydrocarbon has more boiling point than branch chain, because branch chain decreases the surface area, and as the surface area of the compound decreases, melting point, boiling point will be decreased. Okay, and third one is, if the chain length is increases, the chain length of alkyl halide or haloalkane, if the chain length increases, then the boiling point and melting point will also increase. Okay, that's why CH3 CH2 CH2X has more boiling point than CH3 CH2X than CH3X. And see, bond strength of haloalkanes and haloarenes. Bond strength of haloalkanes decreases as the size of halogen atom increases. Thus, bond strength of CH3F, halogen bond strength in CH3F is more than carbon chlorine bond strength, than carbon bromine, than carbon iodide. So carbon fluorine bond is more strong than carbon chlorine, is greater than carbon bromine, greater than carbon iodide. Okay. Now see, chemical properties of haloalkanes and haloarenes. The main chemical reaction of haloalkanes and haloarenes is substitution reaction, SN reaction, nucleophilic substitution reaction. Haloalkanes and haloarenes, they show different types of chemical reaction, like nucleophilic substitution reaction, elimination reaction, and reaction with metals. So first, nucleophilic substitution reaction. Nucleophile will react with the alkyl halide, and nucleophile will substitute the halogen atom from haloalkanes or haloalene. Okay, and here different types of nucleophilic substitution reaction are given. Substrate is ethyl bromide, which is the haloalkane C2H5Br. Now if you use KOH, KOH, the nucleophile will be OH minus, and Br will be substituted by OH group, so you will get alcohol. Now if you react ethyl bromide with ammonia, then you will get ethylamine. The Br will be substituted by NH2 group. If you react ethyl bromide with KCN, then KCN nucleophile is K plus and Cn minus. Nucleophiles are negatively charged ions, are known as electron rich substituent, or electron rich anions are known as nucleophile. Okay, if you react ethyl bromide with KCN, the Br will be substituted by Cn minus, so you will get ethyl cyanide. If you react ethyl bromide with AgCN, you will get ethyl isocyanide, C2H5NC. C2H5NC. All these are nucleophilic substitution reaction. If you react ethyl bromide with KNO2, potassium nitrite, you will get ethyl nitrite, C2H5ONO. And if you react ethyl bromide with AgNO2, you will get ethyl or nitroethane. Okay, so these are some examples of nucleophilic substitution reaction of haloalkanes. Okay, and nucleophilic substitution reaction are two types. One is SN1 type, another is SN2 type. SN1 means unimolecular nucleophilic reaction. Nucleophilic or SN1 means substitution nucleophilic unimolecular. Unimolecular means molecularity is 1. Okay, so SN1 reaction proceed in two steps. It is nucleophilic substitution reaction. In SN1 reaction, in first step, which is reversible, first step is reversible and slow. Okay, in first step, the halogen atom removed from the substrate, and you will get a planar carbocation. So in the first step, planar carbocation is formed after removing the halogen atom from the substrate, from the haloalkane. And in second step, the nucleophile attack the planar carbocation. So SN1 mechanism, it is a substitution reaction of haloalkanes, which is a two-step reaction. Okay, in first step, planar carbocation is formed, and second step, the nucleophile attack the carbocation. Okay, so it is a substitution reaction, and this in this reaction the rate of this reaction depends only on the concentration of substrate. That's why this is unimolecular reaction. In SN1 reaction, the concentration rate of the reaction depends on the concentration of reactant only. Okay, rate of the reaction depends only on the concentration of reactant. That's why it is first order reaction, and molecularity is 1. And reactivity order of alkyl halide towards SN1 mechanism, 3 degree alkyl halide is more reactive than 2 degree than 1 degree. Very important point, remember that. Okay, because this is because in the first step, you know that in SN1 reaction, in first step carbocation is formed, and if the stability of carbocation is high, then the rate of the reaction is also high. And order of stability of different carbocations are positively charged carbon compound. Okay, you know that 3 degree carbocations are more stable than 2 degree carbocation than 1 degree carbocations. That's why rate of SN1 reaction for different alkyl halide is uh, is faster for 3 degree alkyl halide and slowest for 1 degree alkyl halide. Rate of reactivity order of different alkyl halide toward SN1 mechanism is 3 degree alkyl halide greater than 2 degree alkyl halide greater than 1 degree alkyl halide. And polar solvent in low concentration of nucleophile and weak nucleophile favors SN1 mechanism. In SN1 reaction, partial racemization occurs. Racemization, mixture of two products of opposite configuration you will get in SN1 reaction. Mixture. So this is written. Partial racemization occur in SN1 reaction. This due to possibility of frontal as well as backside attack. Due to possibility of frontal and backside attack on planar carbocation. Okay, in the first step, you know, carbocation is formed, and in second step nucleophile attack the carbocation, and there is two possibilities of attack. So frontal attack and backside attack. For these two type of attack, you will get a mixture of two substituted product. Okay, with opposite configuration. That's why this is written as in SN1 reaction racemization occur. Now see second type of reaction, SN2 type, or substitution nucleophilic bimolecular. Substitution nucleophilic bimolecular reaction, molecularity 2. In this reaction, the rate of this SN2 reaction depends on both concentration of reactant and concentration of reagent. Okay, concentration of substrate Rx and concentration of nucleophile. Okay, so rate of this SN2 reaction depends on both concentration of substrate and concentration of nucleophile. Now see SN1, how to proceed SN2 reaction. It is a single step reaction. Nucleophile attack from the backside of the substrate, and a leaving group, the halogen atom or leaving group will be removed from the substrate. Okay, this is a single step reaction, and this is a transition state, highly energetic state. Okay, so in SN1 reaction, backside attack is more important, and in SN2 reaction, backside attack is important. You have to focus on backside attack of the substrate, and in SN1 the carbocation stability is important. Okay, so inverted product. In SN2 reaction, inversion of configuration occur due to backside attack of the nucleophile. So in SN2 reaction you will get inverted product, and in SN1 reaction racemization of configuration occurs. Okay, so in SN2 reaction inversion of configuration is occur, and SN2 reaction racemization of configuration occur. Okay, and now see reactivity order of different alkyl halide toward SN1 mechanism. 1 degree alkyl halide is more reactive than 2 degree than 3 degree, just opposite of SN1. 1 degree alkyl halide is more reactive than 2 degree than 3 degree alkyl halide. And rate of reaction, SN2 reaction, depends on strength of attacking nucleophile and both on the strength of or concentration of attacking nucleophile and concentration of substrate also. Okay, and some common nucleophile are given, attacking nucleophile are given. And non-polar solvent, strong non-polar solvent, strong nucleophile, high concentration of nucleophile favor SN2 mechanism. Okay. And now see relative rates of relative rate of some alkyl halide in SN1 and SN2 reaction. Okay, in SN1 reaction, rate of in SN1 reaction, 3 degree alkyl halide, rate of 3 degree alkyl halide is more than benzylic halide, is more than allylic halide, is more than 2 degree alkyl halide, more than 1 degree greater than methyl halide. And in SN2 reaction, benzylic halide is rate of benzylic halide is more than allylic, is more than primary, secondary, tertiary and quaternary. Okay. So this order you have to remember, rate of different SN1 and SN2 reaction. Okay, and remember that this allylic and benzylic halides are more reactive in both SN1 and SN2 reaction. This is because allylic and benzylic halides are resonance stabilized, and these benzylic carbocations are resonance stabilized carbocation. So these benzylic and allylic halides are more reactive in SN1 and SN2. Now relative reactivity of alkyl halide for same alkyl group. If alkyl group is same, then alkyl iodide is more reactive than alkyl bromide, is more reactive than alkyl chloride greater than alkyl fluoride. Okay. Now next type of reaction of haloalkane is elimination reaction. Elimination reaction. Okay, neutral HBr molecule will be removed from the haloalkane. Okay, it is also known as beta elimination reaction. Okay, when haloalkane is treated with alcoholic KOH, you will get a eliminated product. Okay. The Br atom will be removed and one hydrogen atom will be one hydrogen atom and one bromine atom from the hydrogen atom from this carbon and one hydrogen atom from this carbon will be removed. Okay, so this is elimination product. HBr will be removed from the substrate and you will get alkenes, and major product will be more substituted alkene from one hydrogen atom from this carbon and Br atom from this carbon. If you use alcoholic KOH, you will get elimination product. HBr will be eliminated from the substrate. Okay, and you have to give a double bond. So two type of product you will get, minor product or but 1 and one is another is major product which is but 2 and ease of dehydration of different alkyl halide is 3 degree alkyl halide is greater than 2 degree alkyl halide. Dehydrohalogenation, that is of a elimination order of reactivity order of different alkyl halide is 3 degree alkyl halide greater than 2 degree alkyl halide greater than 1 degree alkyl halide. Okay, now reaction with metals, it is also important. Reaction with metals, three main three reaction Wurtz reaction, reaction of alkyl halide with sodium. Okay, two alkyl halide will react with sodium in dry ether solvent and you will get alkane. Okay, RR, you have to remove 2 NaX. In Wurtz-Fittig reaction, one alkyl halide is, when one alkyl halide is react with aryl halide, you will get aromatic hydrocarbon. Okay, and reaction with magnesium, when alkyl halide reacts with magnesium, you will get ethyl magnesium bromide, that is Grignard reagent. You will get reaction Grignard reagent. Okay, thank you students.